Uh, so hello to everyone who's watching on YouTube. Uh, since no one has joined the session till now, I'll wait for like 3-4 minutes for some people to join the session. If not, I'll just start solving the problem. So I'll start in like 3-4 minutes so that a few people, if they are joining, may join. So yeah. Okay then. Hello everyone. Who is watching on YouTube? So, since no one has joined the session till now, maybe I'll just get started so that we'll have we'll solve the problems and people can view it on YouTube later. So yeah. So first of all, like apologies for starting this session late. Like I had some technical difficulties because the session got delayed by like 40-45 minutes. But I believe still we'll be able to cover all the problems in time because uh, this is the ninth session. In this session, the problems were mostly around Euler circuits and stuff like that, and Hamiltonian circuits. So the problems are quite simple. So I believe we'll be able to cover the problems in the time. So this session will be a shorter one because like we have started a bit late because of technical issues. So I'm right now starting at 6:45 p.m. So yeah, hopefully we'll be able to cover the problems in the next 1.5 hours at max. So yeah. So let me just share my screen and okay, yeah. So first of all, just to reintroduce myself again, I'm Lakshya Sagi, the discrete maths TA for the Tuesday sessions. So yeah. So I guess I'll just start sharing my screen and I can start discussing the problems now then. So yeah. So I'll just share my screen then. So yeah. So hopefully everything should things should be visible to everyone now. So yeah. So let's just get started then. So uh, the first question for uh, today is this. So first question is saying the number of distinct Hamiltonian cycles in a labeled complete graph of 6 nodes is. So I'll be assuming that you guys already know what a Hamiltonian cycle is and like what are Hamiltonian graphs and what are Eulerian graphs because this has been discussed in this week's NPTEL lectures. So yeah, so I would recommend watching those lectures to get an idea of what are Hamiltonian cycles and what are like Euler graphs and stuff. So yeah, so I'm assuming you already know these definitions. So because of shortage of time, there will be no preliminaries list of preliminaries, which I generally discuss before starting the problems. So yeah, I'll just straight away start discussing the problems. So the first question is saying the number of distinct Hamiltonian cycles in a labeled complete graph of 6 nodes is. So the problem essentially says that we need to find the distinct Hamiltonian cycles. So Hamiltonian cycles are the cycles which contain all the vertices of the graph, and the graph is a complete graph. So every pair of vertices has an edge between them. So this is what a complete graph is, that every pair of vertices has an edge between them. So now we want to find the number of distinct Hamiltonian cycles in this labeled complete graph, and this complete graph has 6 nodes. So let's just view the cycle as nothing but a permutation of vertices. Let's just view a cycle as a permutation of the vertices uh, V1, V2. So there are 6 vertices, so I'll just label them V1, V2 till V6. And what I'm trying to say is, so if we permute 2 vertices, let's say I write one permutation which is V1, V2, V3 up to V6, then another permutation of vertices can be V2, V1, V3, V4, V5, V6. So yeah. So what I'm trying to say is if we just list out all the permutations of the vertices of these V1 to V6 vertices, uh, then what can we try to do is maybe relate the number of permutations to the number of Hamiltonian cycles. So this is how we'll proceed. So we will try to mm, okay, then I guess this is a high level idea. I don't need to type it down. So what I'm trying to say is, using these permutations of vertices, I'll try to associate each permutation to some other cycle, like some of the permutations. So basically, what I'm trying to say is, I'll associate some of the permutations to one cycle, that every permutation, like a set of some permutations, will correspond to exactly one cycle of out of all the possible Hamiltonian cycles. Similarly, another set of permutations of these vertices will correspond to another Hamiltonian cycle, and so on. So we will try to associate a set of permutations to exactly one of the cycles out of all possible distinct Hamiltonian cycles. So first of all, uh, first of all, we know that we are sort of seeing the number of permutations of these vertices, which are like from V1 to V6. So we know that number of permutations, like these are six vertices. So we sort of know that the number of permutations will be nothing but, like from previous lectures, we know that number of possible, so number of possible permutations is nothing but 6 factorial for 6 vertices. And now what we'll try to do in our solution, uh, now we will try to associate a set of permutations to basically one of the cycles of these out of all possible distinct Hamiltonian cycle. We'll associate another set of permutations to another cycle, and so on. So basically what I'm trying to say here is, so let's just consider this permutation of V1 to V6, right? So we have labeled these vertices as V1, V2, V3 up to V6. Now what I'm trying to say is, uh, this permutation of V1 to V6 will correspond to one Hamiltonian cycle in which these vertices V1 to V6 occur in this order, right? And now what I'm claiming is another permutation, which is V2, V3, V4, V5, V6, comma V1, will also correspond to the same cycle. So what I'm trying to do here is, so we sort of see one of the cycles of the graph, and we just see what are the possible labels of the vertices on that cycle. So so maybe just to give you guys an intuition, so we can see that uh, V1, V2 up to V6 maybe I should send it here, and yeah. And V1 to V6, then we can see that the permutations V1 to V6, and then the permutation which starts from V2, V2, comma. Maybe I'll just for the sake of clarity, I'll just put these permutations in parentheses so that you don't get confused. Like where are these permutations separated? So yeah. So the permutation V1 to V6, then the permutation which starts from V2 and till V6, and then ends at V1. So I hope you guys must have seen cyclic permutations. So this is sort of that sort of concept only. Uh, like what I'm trying to say is, we see this permutation which starts from V1, which considers the vertices in this order V1, V2, V3 till V6. Similarly, we see another permutation which considers the vertices in other order, where it starts from V2, then goes to V3. So basically, these two permutations just differ by the starting position. Like this permutation and this permutation are essentially the same. The only difference being that the V1 here, this permutation started from V1. So that's why the order here was V1, V2, V3, V4, V6. But in this permutation, it starts from V2. So order will be first going from V2 to V6 and then arriving at V1. Similarly, another permutation can be where we start from V3 instead and we go till V6. And after going to V6, again, like this order will again come. So this order of like going to V6 and then going to V1 and then V2. So these three permutations, and similarly, there will be actually six permutations because similarly we can start from uh, V4. Similarly, we can start from V5. Similarly, we can start from V6 as well. So the final sort of, and after going starting from V6, we'll again start from V1, which will give us this permutation only. So after starting from V6, we can have the permutation go to V1 and then straight up go to V5. So yeah. So so all these permutations, as we can see, if we label the vertices on a cycle, like I'm not able to draw a cycle because I don't have any pad here, uh, writing pad here. So this permutation of going from if we label the vertices on the cycle, then this permutation of vertices, like labeling the vertices in this order on the cycle, if we just label the vertices in this order, V1 to V6, then this label of V2, V3 till V6 and then V1 will also correspond to the same cycle. The only change will be the only change is here is because we have started counting, or we have started noting from the second vertex instead of the first vertex itself. Similarly, if we start from third vertex, it will be nothing but V3, V4, V5, V6, and then we come to V2, V1, V2. Similarly, this permutation, although all these permutations are distinct, but it can be noted that all these permutations will correspond to the same cycle. Like in the last permutation here, we had just started counting from V6 and then we came across V1 because the order of V1 to V6 is maintained in the cycle. And then we counted till V5. So all these permutations correspond to the same cycle, correspond to the same Hamilton, correspond to exactly one Hamiltonian cycle, exactly one Hamiltonian cycle. So we sort of see, so there were earlier 6 factorial possible permutations, but we must have seen this sort of thing in cyclic permutations. This is the same concept as in cyclic permutations, that actually all of these cycles uh, will actually correspond to the same cyclic permutation. Like all of these permutations will correspond to the same cycle. And these are 6 permutations. So we sort of see that the number of possible cycles, the number of permutations were 6 factorial, but but we know that at least 6 permutations, 6 of these permutations correspond to the one cycle and not more than one. And there were 6 factorial permutations. So the number of cycles will be something like 6 factorial divided by 6. Because we know total number of permutations, but for all these permutations, at least 6 of those permutations correspond to one of the cycles. So that's why number of cycles will be at max limited by 6 factorial by 6. But note that we are still not done here because another observation is uh, another observation is just pointing it out. So we need to find the number of distinct Hamiltonian cycles, right? And we know that this V1 to V6 forms the cycle. Similarly, this V forms one cycle, and that cycle corresponds to this permutation also, and so on. But what I'm trying to claim here is consider the cycle formed by the vertices in the reverse order. this will also, what I'm trying to claim is, the cycle which has the vertices in this order v1, v2, v3 till v6 will also correspond to the cycle which has the vertices in the reverse order. Because in a like because since this is a graph, the edges can be what I'm trying to say is the edges can be traversed in any possible direction and we'll get the same cycle essentially because the same set of vertices will be covered in sort of same order. So what I'm trying to claim is if I start from V6, then I go to V5, then I go to V4, then I go to V3, V2, V1, that will be actually the same cycle as the cycle of V1 to V6. So another observation is that uh, V1, V2 till V6 will also uh, so V1 to V6 and the permutation of uh, V6 to V1. So this was so basically the permutation which is its reverse. So I'll just write it first that permutations which are reverse of each other will correspond to the same cycle. So what I'm trying to claim is so first we claim that the permutations of these type will correspond to exactly one Hamiltonian cycle. So there were 6 factorial possible permutations. So since 6 of these corresponded to one cycle, so we'll divide 6 factorial by 6, first of all, to find the number of cycles. So this part will be taken care of by dividing 6 factorial by 6. Now what I'm trying to claim is doing this is not enough. We'll have to divide by another factor of 2. We have to divide the answer by a further factor of 2, which is because permutations which are reverse of each other will also correspond to the same cycle. And for an example, uh, that is V1 up to V6 and the permutation V6 V1 till V5, or maybe V6 V5 V4 V3 V2 V1 V6 V5 V4 till V1 will correspond to the same Hamiltonian cycle. And why is this? You can see whenever you draw a graph, if we draw a graph, uh, first of all, if we label the vertices as V1 to V6, all these permutations will exactly correspond to the same cycle. And that cycle can also be obtained by counting the vertices in their reverse order, in the reverse. So in first we count the vertices, let's say in clockwise direction. First we count the vertices of that cycle in clockwise direction. So the only way I can sort of change the permutations is by changing the starting point. So I'm going clockwise only. So this order of V1 to V6 has to be maintained, but the starting point of my clockwise counting can change. So I started from V1, so I obtained V1 to V6. Then I started from V2 and I obtained this one. Similarly, I started at V6 and I obtained this one. But now what I'm trying to do is now I can also count in the cycle along anti-clockwise direction also, right? So if I have some cycle in the graph, so we can sort of easily see that this cycle which goes from V1 to V6, if this is in the clockwise direction, it will be actually the same cycle from which is V6 to V1 if the same cycle has counted from in the anti-clockwise direction. So instead of counting from V1 in the clockwise direction, I counted from V6 in the anti-clockwise direction. So the cycle is same because actually the graph is undirected, we know. So in an undirected graph, the direction of edges doesn't matter, right? The edges can go along both ways. So that's why we can count in clockwise direction as well as anti-clockwise direction. So while counting from clockwise side, we obtain this cycle, and counting the same cycle in anti-clockwise side, we obtain this permutation. So these two permutations, so permutations which are reverse of each other, the only difference is one starts counting in clockwise, one starts counting in anti-clockwise. So because of this, the actual number of cycles will for obtaining the actual number of cycles. So from this, we sort of obtain that uh, the number of permutations is double of number of Hamiltonian cycles, right? And this is independent of this factor where we obtain that the number of permutations need to be divided by a factor of 6 to obtain the cycles. And now what I'm trying to do is, even after dividing by 6, we have not taken care of the clockwise anti-clockwise thing. So that's why we'll sort of need to divide by a further factor of 2. So we'll need to divide the number of permutations by a factor of 6. So first of all, we divide by a factor of 6. And this is sort of easy to see. You sort of have seen this in cyclic permutations also. Now, the next observation is that permutations which are reverse of each other also correspond to the same Hamiltonian cycle. So because of this, we'll need to divide. Because of this, we'll need to divide by a further factor of 2. So essentially, given the number of permutations, which are 6 factorial, out of these 6 factorial permutations, like we can always group the 6 times 2, which are 12 permutations. And these 12 permutations will be actually be corresponding to the same Hamiltonian cycle. So one Hamiltonian cycle can be denoted by 12 of these permutations. So because 6, because we can change the starting point, and this factor of 2 because we can count in clockwise or anti-clockwise direction. So basically 12 of these permutations correspond to one Hamiltonian cycle. So the final answer will be, so like just laying down the answer, or so essentially 12 permutations correspond to exactly one unique. And why is it unique? Because in cycle, we can only count in clockwise or anti-clockwise direction. And there are only 6 possible ways of starting the counting. So yeah, we have exhausted all the possible ways. And from where I obtained this number 6, this number 12, I obtained this by a factor of 6 times 2. Because of this 2 and because of this 6. Correspond to exactly one unique Hamiltonians. Or maybe I should delete this line. Yeah. So essentially 12 permutations correspond to exactly one unique Hamiltonian cycle. So number of distinct Hamiltonian cycles is nothing but the number of permutations, which are 6 factorial, divided by this number 12, which is because the total number of permutations were 6 factorial, but 12 of these correspond to one cycle. And so we need to find number of cycles. So we'll just divide 6 factorial by 6. So this will be something like 6 factorial divided by 12 will be nothing but 60. So yeah. So correct answer is actually hence option D is the correct answer. So just to note, since we were given six vertices, we were given just six nodes, we were able to obtain this answer of uh, 60 here. So if we were instead given n nodes, not just six nodes, we can generalize this solution to n nodes also. So if we are given the nodes v1 to vn, the number of permutations will be n factorial. But out of these, n, because of this factor, n of these permutations will correspond to one cycle. And similarly here also like uh, two, because of this reasoning, further two permutations will correspond to the same cycle. So we'll sort of need to divide n factorial by a factor of 2 times n, which will be actually equal to, uh, so maybe I should write it down. So this will actually be equal to n minus 1 factorial divided by 2. So just putting a note out there. So note, in the above question, if we were instead given n nodes, then the answer would have been n minus 1 factorial divided by 2. And how do we obtain this? We obtain this by n factorial divided by 2 times n. Yeah. Or maybe just n factorial by 2n. Yeah. Using the same arguments as a, because there will be this n factorial is obtained by n factorial possible permutation. This factor of 2 is because of clockwise and anti-clockwise, and this factor of n is because of the offset. So whether we start counting from v1, we start counting from v2, or we start counting from vn. So yeah. So yeah, this is just an added part which I just mentioned to everyone. So yeah. So now for the second question then. So we have covered the first question. So the second question says select the correct options. So note that yeah. So the second question says a graph with Euler path can have a degree sequence of 4, 4, 4, 3, 3, 2. So we know from the lectures that maybe just I'll start with option A. We know from the lectures that a graph has an Euler path if and only if uh, basically a graph has an Euler path if and only if there are exactly two vertices with odd degree in it. So a graph will have an Euler path if and only if there are exactly two vertices with odd degree in it. Maybe I should mention this in the preliminaries because this has been discussed in the lectures. Or maybe, yeah, I should put this, I guess. So just writing it out here for everyone to see. A graph has an Euler path if and only if there are exactly two vertices with odd degree in it. Similarly, a graph has an Euler tour or it is Eulerian. Like a graph is Eulerian. Note that a graph having an Euler path is different from graph being Eulerian. So these are two different properties. And a graph is Eulerian if and only if all vertices have and even degree. So a graph is Eulerian if and only if all vertices have an even degree, and in no other case is it Eulerian. So these are the two properties which will be used in the question which I'll just start the second question basically. So yeah. So the second question says a graph with the Euler path can have a degree sequence of 4, 4, 4, 3, 3, 2. So degree sequence is nothing but degree sequence denotes the degrees of vertices in the graph. So as we can see here, for checking for an Euler path, we just need to check whether there are exactly two vertices with odd degree. And we can see there are only two vertices which have odd degree, which is a degree of 3, and all other have even degree. So yeah, so option A is correct. So option A is correct, as exactly two vertices have an odd degree equal to 3. So yeah, that's why option A is correct. Similarly, option B says graph with degree sequence 2 to 2 to 2 can be Eulerian. So yeah, this is also correct as for a graph being, as we showed that for a graph to be Eulerian, all the vertices need to be of even degree. And here, since all vertices have a degree of 2, 2 is an even number. So yeah, as all vertices have an even degree equal to 2. Yeah. So now option C says an untitled simple graph with degree sequence 1, 4, 2 can be Eulerian. So note that this is uh, not true. This statement is incorrect because for a graph to be Eulerian, we need all the degrees to be even. But here we can see that the first vertex has a degree of 1, which is odd. So this graph will not be Eulerian. Incorrect, as one vertex has an odd degree equal to 1. So yeah. So this was a fairly simple question. We just need to know the properties. And if we know the properties, we can easily see. So option D, none of the given statement is true, is essentially incorrect, as we can see, because option A and B are correct. So yeah. So option D, I just write down for sake of completeness. Incorrect. So hence option A and option B are correct. So this is the correct answer. Okay, I hope this was simple. So now let's come to the third question. The third question says, so what is the vertex chromatic number of an n vertex simple undirect simple connected graph which does not contain any odd length cycle assuming n is greater than equal to 2? Okay, so this is a bit of an interesting question, or maybe not so much. Like we'll just see. So what is it saying? It's saying that we need to find the vertex chromatic number. So we know from the lectures what is the vertex chromatic number. So vertex chromatic number is the minimum possible colors by which we should color the vertices such that no two adjacent vertices have the same color. So this is what a vertex chromatic number is. So we need to find what is the vertex chromatic number of an n vertex graph where n is greater than equal to 2, such that the graph does not contain any odd length cycle. So we are sort of given that the graph does not contain any odd length cycle. So just mentioning to you guys, so uh, actually the graphs which have this property that they do not contain any odd length cycle are called bipartite graphs. So answer is, so let me just discuss the answer. The graphs which do not contain any odd length cycles are called bipartite graphs. Or maybe not just called, like the graphs which do not contain any odd length cycle are bipartite graphs. So what is exactly a bipartite graph? So uh, what I'm trying to say is this property that if a graph does not contain any odd length cycle, then it is bipartite. So maybe I should write this better. If a graph does not contain any odd length cycle, then it's a bipartite graph. And like, why do I mention this? Like, why is it a specialty? Like, what's so special about bipartite graphs? So, if some of you must already know what a bipartite graph is, but just for others to know, so I'll just mention this orally. Like, a bipartite graph is nothing but a graph in which we can sort of, uh, okay, so maybe I should write down. A bipartite graph is a graph in which the vertex at V can be partitioned into two disjoint sets, U and W, such that all edges of the graph have one endpoint in U and other endpoint in V. So the definition for bipartite graphs is very simple. It may seem like with too much notation, it may seem confusing, but I'll just show you one example of a bipartite graph and you will be able to easily see what a bipartite graph is. So this is something which you should trust me, like this first claim that if a graph does not contain any ordinate cycle, then it's a bipartite graph. I won't be showing you this, but just assume it's a property. Like whenever you see a graph which does not contain any ordinate cycle, just think of replacing that with the bipartite graph. Like it's equivalent. A graph which does not contain any ordinate cycle is actually equivalent to a bipartite graph. So yeah. Just always think of a graph which does not contain any odd length cycles as a bipartite graph only, and not like like this definition need not be used. You can just use the bipartite graph definition. So yeah, a bipartite graph is a graph in which the vertex set V. So we can divide the vertex set V into two disjoint sets U and W, such that all edges of the graph have one endpoint in U and the other in W. So what this means is that no, there cannot exist an edge between, let's say, two vertices of U or between two vertices of W. And why is it so special? Like, why does this help us that there are no two edges in U and no edge goes from between two vertices of U and two vertices of W? So we can sort of denote, let's say, U as we can sort of denote the graph uh, like this. Let me just show you. Uh, just give me. So yeah. So what I've sort of done here is like let's just say this was my initial graph, and this is actually a bipartite graph. Let's just say this is a bipartite graph because you can see that let's just assume the red colored vertices are the vertices of the set U, and the blue colored vertices are the vertices of the set W. Then we can see that all edges are going from U to W only. No edge goes between U, any two vertices of U. No edge goes between any two vertices of W. And what's the advantage of this? We can sort of put all the vertices of U on one side. We can put all the red colored vertices on one side, all the blue colored vertices on other side, and we can sort of like just assume this. We can sort of denote the graph very easily. Like the intuitive representation is like all the vertices on the upper side don't have any edge between them. All the vertices on the lower side don't have an edge between them. And just the vertices which are the vertices which can have an edge between them are the vertices where one vertex is on upper side and other vertex is on lower side. So yeah. So this is a diagrammatic representation. This is a diagram example of bipartite graphs. And like you can see, it has a very simple structure actually. If we see in diagram that take one set of vertices on the upper side, the other set of vertices on the lower side, and then we just need to draw edges from upper to lower. Like upper to upper edges are not allowed and lower to lower edges are not allowed. So yeah. So this is an example of a bipartite graph. So yeah. And what's so special about the bipartite graph? So I hope you guys must see that I have colored the vertices as the vertices, some vertices, the upper side vertices have been colored as red, and the lower side vertices have been colored as blue. And what we can claim here is actually this is a perfect, like this is a valid vertex coloring. I hope everyone is able to see this. Like this is actually a valid vertex coloring because a coloring of a word, like a coloring is a valid coloring, a vertex coloring is a valid vertex coloring if no two adjacent vertices have the same color. And we can see that since all edges are going, all edges will have one endpoint in U and other in W, then if we color all the vertices of U by one color and all the vertices of W by another, we know that there are no edges from U to U and from W to W. Then we can clearly see that we'll just need two colors at most, always. So we'll just need two colors. The upper side by one color one and the lower side by the second color, and we'll always have a valid coloring. So vertex chromatic number of a bipartite graph, a bipartite connected graph. So this graph is connected. So suppose there was no edge present, like suppose this was an unconnected graph, then suppose there was no edge present between upper and lower side, then all the vertices can be colored by the same color, right? Because if no edge is present in the graph, only vertices are present, then I can just color every vertex by the same color and it will be a valid coloring. So we are assuming that the graph is connected at least. So since the graph is connected, we can color the upper side by one color, lower side by another color, and we'll always have a valid color. So by using just two colors, we can always color a bipartite graph. So that's the beauty of bipartite graphs. In a general graph, we can require, you may have seen in the lectures, as much as like or n colors, but in a bipartite graph, I'll just need at max two colors. So we can, or maybe I should write it like this. It can be seen maybe here I should first denote the equivalent definition. So all edges of the graph have one endpoint in U and other in V and other in W, sorry. And how does this help us? That is no edge exists between two vertices if both the vertices belong to U or both belong to W. So if both belong to U, both vertices belong to U, or both vertices belong to W, then there can be no edge between such pair of vertices, no between such pair of vertices. And that's why we were able to color the whole set U by one color and whole set W by the other color. So yeah. So it can be seen that we can color the vertices in U by one color and the vertices in W by another color. And from this, will be, and this will be a valid coloring. And this will always be a valid coloring. Okay. Okay, maybe I should just have one spelling for color, otherwise it will just show spelling mistake. So, so yeah. So this will always be a valid coloring. So basically, a simple connected bipartite graph has a hence a hence a connected bipartite graph has vertex chromatic number equal to 2. So that's the beauty of bipartite graph, that a connected bipartite graph can always be colored by uh, two colors. So B is the correct answer, like B option is 2. So yeah, hence option B is correct. So yeah. So I hope everyone appreciates the beauty of bipartite graphs. Like they are essentially in a lot of context in computer science. So yeah, so you should be familiar with bipartite graph and their properties. So yeah. So let's just come to question 4. Let's come to question 4 then. So the question 4 says a graph G is obtained by adding vertex V to K13. So what is K13? K13 is this graph which I have drawn. Like I mentioned this in my previous session also, that K13 is a notation and it denotes this sort of graph. And note that this graph is also bipartite. Why? Because you can take the vertex 1 on one side and the vertices 2, 3, 4 on another, and we have only edges from this side to this side. So yeah, so this is a bipartite graph actually. So a graph G is obtained by adding the vertex V. So we had this K13, and now the problem is saying that to obtain graph G, we add a vertex V to this K13 graph and make V adjacent to every vertex of K13. So we sort of take a vertex V and add an edge to every vertex of this K13. And now what is the minimum number of colors needed to edge color this G? So the problem statement asks, like, what is the minimum number of colors which we need to edge color G? Right. So edge coloring, I hope everyone knows, this has been discussed in the lectures, that like earlier I mentioned vertex coloring. Vertex coloring was how the vertex color was the minimum number of colors needed to color the vertices such that no two adjacent vertices have the same color. In edge color, it's similarly defined as minimum number of colors needed to color the edges so that uh, two edges, two edges which have a common vertex do not have the same color. Like basically adjacent edges do not have the same color, something like that. So what in vertex coloring, adjacent vertices do not have the same color. In edge coloring, adjacent edges do not have the same color. So note that these are two different concepts, the edge color and the vertex color. Like in this bipartite graph, we can see that vertex color is always 2, but edge color can be a lot more than 2. So yeah, in general, just keep this in mind that edge color is a lot different from vertex color. So yeah. So this was the graph which was like, this is the graph which was initially like we were given K13 and then we added a vertex V and made V adjacent to every vertex of K13. So after this, the image will look something like this. Let me just add the image. Okay. So this will be what the image looks like. This is what the image looks like. So yeah. So we had this K13 graph. The solid edges denote the initial K13 graph. As you can see, like 1, 2, 3, 4. Here, this is 1, 2, 3, 4. And then I added a vertex V and made it adjacent to all the vertices of this K13. So I sort of added these 4 edges because there were initially 4 edges. So this is the graph G, which I obtained. So, yeah. So this is my graph G actually. And now I sort of need to find so we need to find the minimum number of colors needed to edge color G, right? So in this graph, we'll sort of need to find the minimum number of colors needed to edge color G. So since this is a very small graph, like this only has 5 vertices, like I don't want to show you guys how to color, like it can be seen we need to color these 4 edges at least which are adjacent to V with different colors because they share the common vertex V. And then by some other constraints, you can actually show that there will need actually 4 colors only. So my claim is we can edge color G with 4 colors. So this is the claim, and you should try it yourself. It is easy. Try it yourself. So, uh, so you can show this yourself that we can actually edge color G with 4 colors. But note that we need to find the minimum number of colors needed. Like just showing that we can color with 4 colors does not prove that this is also the minimum possible, right? Minimum possible can be 3, can be 2, can be 1 also. So it can be anything, but if we just show that we can edge color with 4 colors, then I'm claiming that any coloring, any edge coloring will actually require 4 colors at least. So this claim is something which you should show yourself. Like you should just try to edge color G using 4 colors. And I'm pretty and you will be able to obtain one such coloring. And now what we claim but we also need to show that this is the minimum possible, right? We just because we need to find a proof that this is minimum possible. So one thing is in any graph G, the edge chromatic number, like edge chromatic number is just the minimum number of colors need to color G. Edge chromatic number is at least greater than equal to, we can always say in any graph G, edge chromatic number is greater than equal to maximum degree. Maximum degree in graph G, maximum degree of a vertex in graph G. So, or maybe in G. So what I'm trying to claim here is edge chromatic number will at least be I'm not saying it will be actually equal to because it may not be equal to. You will need sometimes you will also need more colors. So that's why I have this inequality and not equality. But what I'm claiming is this edge chromatic number will always be at least as large as maximum degree of a vertex. So basically what I'm trying to claim is just see the graph G and note the degrees of all the vertices in G, and then the maximum degree will be at least a lower bound on the edge chromatic number. And why is this the case? Just consider this graph only, the graph G only. So we know that consider any vertex. So consider any vertex, like let's just say consider V. So we know the degree of V is 4, right? Because 4 edges originate from V. And now we can be sure that these 4 edges which originate from V will require different colors, right? Because all of these edges have an endpoint, common endpoint in V. So all these edges will require different colors. So that's why we'll need at least degree of V colors. Similarly, we'll also need at least degree of one color, degree of two, degree of three, degree of four. And so we'll sort of need at least the maximum degree, the colors which correspond to the maximum degree. And here in this graph, it can be seen. So like the proof for this statement is pretty easy because for any vertex V, this is because for any vertex V in G, uh, uh, all edges incident to V will need to have different colors. So that's why this statement is true. And now because of this statement, we can say okay, so maybe I should have this as a separate property because you guys may get confused by the G I use here and the G used in the question. So yeah, I should have this in preliminaries instead. Yeah. In any graph G, the H chromatic number is greater than equal to maximum degree of a vertex in G. Right. So this is sort of a preliminary and it is a very important property used in computer science. So yeah, just keep this in mind. And note that there is an inequality here because this is not an equality because there will be instances in which H chromatic number will actually be greater than maximum degree and not equal to. That's why I put a greater than equal to sign. So we sort of showed that H chromatic number, since if we are able to show that we can H color G with 4 colors, then we essentially show that the minimum number of colors needed will be at least 4. H chromatic number is less than equal to 4. Since H chromatic number is the minimum colors needed. Right. So we know that H chromatic number is less than equal to 4. Also, we know that H chromatic number is greater than equal to like we had. So we showed an upper bound by finding a valid coloring of 4 colors, and we also know the lower bound that H chromatic number is greater than equal to maximum degree in G. We know this from our preliminaries, right? So basically maximum degree in G in this graph G, we can see that the vertex 1 has a degree of 4, vertex V has a degree of 4. This vertex 4 has a degree of 2, 3 has a degree of 2, 2 has a degree of 2. So the maximum degree vertices are the vertices 1 and V, and both have a degree of 4. So the lower bound is actually 4. So this implies that H chromatic number in G is greater than equal to 4. So note that we using an example of coloring with 4 colors, we showed that H chromatic number is less than equal to 4. And by using this general theorem, let's just say this is a theorem that H chromatic number is greater than equal to maximum degree, we showed that H chromatic number is also greater than equal to 4. So we showed a lower bound of 4 and we also showed an upper bound of 4. Upper bound of 4 was proved by an existence of a coloring with 4 colors, and the lower bound of 4 was proved by just this maximum degree argument. So I hope the flow of the solution is clear to everyone. So yeah. So this implies that like we showed a lower bound of 4 and we showed an upper bound of 4. So this implies that H chromatic number of G is equal to 4 is actually equal to 4 because we showed a lower bound of 4, we showed an upper bound of 4. So yeah. So the minimum number of colors needed to edge color VV, edge color G is equal to 4. Hence, minimum number of colors needed to edge color G is equal to 4. So this is my final answer. So let's just come to the next question then. So next question is pretty easy also. Next question is just based on direct properties discussed in the lectures. So yeah. Maybe I should. Yeah. So the last question, like this fifth question is the last question for the day. So yeah, I hope we'll be completing on time. So the next question says consider the following two statements. So we are given these statements A and B, and we just need to say whether statement one is true or statement two is true. Like we just need to find out if statement A is true or false, and similarly if statement B is true or false, right? So let's just take the statement A. So statement A says that adding an edge between the odd degree vertices in a connected multigraph having an Euler path will result in a Euler circuit. So the first statement is essentially saying that if we add an edge between odd degree vertices in a connected multigraph which have an Euler path. So basically we are initially given a connected multigraph which has an Euler path, and then we add an edge between the odd degree vertices. And now we want to see whether this will result in a Euler circuit. So I hope the question is clear to everyone. So we are given a connected multigraph which has an Euler path, and then we add an edge between odd degree vertices, and we want to see if this will result in a Euler circuit. So what I'm claiming is this statement is correct. Statement A is correct. And why is this correct? Or maybe I should not just write down correct, but I should first give some explanation and then. So we are given a connected multigraph having an Euler path. Since a graph, so we are initially given a graph having an Euler path, right? Having an Euler path. So we discussed in the preliminaries initially, like I mentioned, that a graph is an Euler path if and only if there are exactly two vertices with odd degree, right? So a graph is an Euler path if and only if there are exactly two vertices with odd degree. And in the question, we are given that the graph has an Euler path. We are given that connected Euler path, graph has an Euler path, and then we add an edge between odd degree vertices. So since a graph having an Euler path has exactly two odd degree vertices, we are just adding exactly one edge which connects these two odd degree vertices. Or maybe between these two odd degree vertices. Right. So we are going to be given a connected multigraph having an Euler path. From this, we know that the graph is exactly two odd degree vertices, and now an edge is added between the odd degree vertices. So since there are only two vertices, so we have just added exactly one edge between these two odd degree vertices, right? So after adding this edge, you can see. So after adding this edge, the degree of these two odd degree vertices increase is by one each. So essentially, let's say both vertices had a degree of 3, or let's say one had a degree of 3 and one had a degree of 5. both had some odd degrees. Now, after adding this edge, both of these vertices have one more neighbor, right? So their degree increases by 1. And so now let's say earlier one of the degrees was 3, it becomes 4. Similarly, one of the degrees was 7, it becomes 8, and so on. So basically earlier degree was odd and now it increases by 1. So now what the degree becomes even for both the vertices. Hence, degree becomes even for both the vertices. So note that initially these two were the only, since the graph exactly had two odd degree vertices. So initially only these two vertices were the one. Let's say the vertices are u and v. So only u and v were the vertices which had odd degree. All of the vertices had even degree, and we added an edge between u and v. So now degree of u and degree of v now becomes even. So now in the updated graph after adding the edge, degree of every vertex in the graph has become even, because these were the only two odd degree vertices, and these two also now have even degree. So every vertex now has odd even degree. So hence, so degree of every vertex becomes even now. So for every vertex, the degree becomes even now. I guess it's too easy to see because earlier we had only two odd degree vertices and we added an edge between them. So their degree becomes even, and all of the previous vertices have degree unchanged, which was even already. So yeah. So every vertex now has a degree of 1. Has an even degree. So yeah. So because of this, so now as degree of every vertex has become even, what property we can say if every vertex has an even degree, like I discussed these in preliminaries, that if all vertices have an even degree, graph is Eulerian. So essentially, the graph becomes Eulerian. Hence, the graph becomes Eulerian. Yeah. So hence the graph becomes Eulerian after adding the edge. And what's the property of an Eulerian graph? This has been discussed in the lectures. So an Eulerian graph is nothing but a graph uh, which has an Euler circuit. A graph containing an Euler circuit is an Eulerian graph. So as an Eulerian graph contains an Euler circuit, so the resulting graph becomes Eulerian, and now we know that Eulerian graph has an Euler circuit, right? So essentially, adding this edge actually results in a Euler circuit. Earlier, there will not be any Euler circuit, but now since we have added an edge, all the vertices become even, so the graph becomes Eulerian. And we know that a graph is Eulerian if and only if it contains an Euler circuit. So the resulting graph will definitely contain an Euler circuit. Contains an Euler circuit. So as an Euler graph contains an Euler circuit, statement A is correct. So I hope you see the flow of the arguments. Initially, we established that there are exactly two odd degree vertices. Then we add an edge between them. So all the vertices now have even degree. Since all vertices have even degree, the graph becomes Eulerian. And an Eulerian graph we know has an Euler circuit. So that's why statement A is correct. So now let's come to statement B. Statement B says a graph G having n vertices with vertex chromatic color M, vertex chromatic number M, has at most M times M minus 1 by 2 edges. So the graph, so the statement 2 says a graph which has a vertex chromatic, which has n vertices and has a chromatic number of M, vertex chromatic number of M. Note that this is not the edge chromatic number, but rather the vertex chromatic number. Like this state, so yeah. So if a graph has vertex chromatic number M, then it has at most m minus 1 by 2 edges. So this is the claim from statement B, that if a graph has n vertices and vertex chromatic number m, then it has at most m minus 1 by 2 edges. Right? So what I'm claiming is this statement is incorrect. And why is this incorrect? We can actually draw a counterexample for this. So incorrect, as we can find a counterexample for the same. And what's the counterexample? Actually, you have already seen the counterexample for this claim. Like we, so let's just see this graph, this bipartite graph. Let me just copy and paste it again here. So yeah. Maybe I should put the poll question on the next first. So yeah. So let's just see this graph, this bipartite graph, and I'll label this as a counterexample of statement D. And why is this a counterexample? As we had already discussed that this graph has a vertex color of 2, right? Because like upper side, this is a bipartite graph. And like one side can be colored with red color and the other side can be colored with blue color. So the vertex chromatic number for this graph is 2. So a graph G having n vertices with vertex chromatic number m, here in this graph, m is equal to 2. So this statement says that if the vertex chromatic number is m, then it should have at most mm minus 1 by 2 edges. So if it has a vertex chromatic number 2, because m is equal to 2 in the bipartite graph, then it should have at most 2 into 1 by 2, which is just 1 edges. So a graph G with n vertices with vertex chromatic number 2 has at most 1 edge. But we know that this graph we can see has a lot of edges. Like there can be edges from this side to this side for every pair of vertices. So this graph you can easily see has more than 1 edge. So this statement is incorrect. So let me just tell you guys. So in the above figure, m is equals to 2, but number of edges in G is greater than 2 times 2 minus 1 by 2. Right? So that's why this is an counterexample. So that's why statement B is incorrect. So statement B is incorrect, only statement A is correct, which means that 1 is true and 2 is false, which is option 1. Maybe I should mention this. This is A and B, not 1 and 2. So statement A is true, but statement B is false. So this is the answer. So hence option A is correct. Option A says that statement 1 is true and 2 is false. So option A is actually correct. So yeah. Okay, so this was the final question which we had for the day. And I guess since I've discussed all of these, so yeah, we are done for the day. So since no one has joined the session, I'll just thank everyone who's watched on you who's watched this session on YouTube. So thanks everyone for watching this session, and I hope you guys will tune in into the meeting next week rather than watching on YouTube, so that we can have a bit more interaction. So yeah, so thanks for watching, guys. So we'll hopefully see you guys in the meet next week, same time like Tuesday 6 to 8 p.m. So yeah, so I guess I'll just stop sharing and close the session for now. So yeah, thanks for watching, guys.